Welcome, everyone, to everything you wanted to know about PCIe, but were too proud to ask. This webinar series is presented by SNIA Data Storage and Networking Forum. I'll be your moderator today. My name is Tim Lustig. I'm pleased to introduce you to our industry expert and speaker for today's webinar, Martin Chow. Martin works with Broadcom's Data Center and Solutions Group as a principal R&D application engineer. A little bit about SNIA before we jump into this. SNIA is an industry organization that develops industry standards and delivers education on data storage and networking technologies. SNIA is comprised of over 200 industry-leading organizations and has over 2,000 active contributing members and over 50,000 participating IT end users and technologists worldwide. SNIA Data Storage and Networking Community, or DSN for short, is the vendor-neutral group within SNIA that provides education and insights for networked storage standards and related technologies for a wide range of end-to-end solutions. Before we jump into the presentation, I wanted to cover a few of the logistics. Real quickly, the slides for this session are available under the attachment tab on the console in your browser window. We'd like this presentation to be interactive, so if you have questions during the presentation, please go ahead and ask them at any time. You can do that by typing your questions into the chat feature. We'll try to answer all questions during the webinar. If we don't have time to get to some of the questions, there will be a Q&A or question and answer blog that will be posted a few weeks after the webinar. Your feedback is important to us, so please take the time to rate the session before you leave. This includes if you are leaving early for some reason. We take your feedback seriously. It is used to improve future webinars and to make sure that you're getting the most out of each session. If you'd like to interact with the industry experts like the presenters of today's session, consider joining SNIA and the DSN community. One last thing before we jump into this, there's a SNIA legal notice. We just wanted to call your attention to this. Basically, it says that SNIA copyright notification regarding the use of the presented material. SNIA is not providing any legal advice, and there are no warranties expressed or implied. And if you do reference this material, you do so at your own risk. And real quickly, I just wanted to cover the agenda. Martin will be covering the PCI Express overview, which will include enumeration, AER, DPC, and hot plug capabilities, non-transparent bridge, as well as SRIOV, PCIe Switch in AI applications, and new and PCIe Gen6. At this moment right now, I'd like to turn it over to Martin. Martin, please take it away.
Thank you. Okay, let's start with the PCI Express overview first. Before talking about the PCI Express, let's look at the legacy PCI first. PCI is an abbreviation of the Peripheral Component Interconnect. 20 years ago and earlier, PCI was standardized the parallel interface primarily designed for motherboard components, connecting various elements like a graphic card, Ethernet card, storage device, and so on. Then PCI Express or PCIe brought a major shift in how our computer components communicate. It moves away from the older parallel bus models and transitioned to the much faster serial bus interface. This serial interface design is like several others, such as SATA, InfiniBand, and Fiber Channel. PCI is designed to back compatible with existing legacy PCI software models. Moving on, let's talk about the evolution of the PCI Express, specifically its different generations. PCI has evolved through several generations so far, starting from Gen 1 and all the way up to the Gen 6. And the Gen 7 spec was also released just 1 month ago. A key takeaways here is that for every new generation of a PCIe, the bandwidth has effectively doubled, allowing for ever-increasing data transfer rates. Beyond just the speed, the encoding method has also changed across generations, which is important for how efficiently data is transmitted. Gen 1 and Gen 2 both utilize the AB10B encoding scheme. This means for every 8 bits of the actual data, 10 bits were transmitted, with the extra bits used for things like clock recovery and basic error detection. With Gen 3 and continuing through the Gen 5, the encoding method shifted to the 128-bit, 130-bit encoding. This is a more efficient scheme, where only 2 extra bits are added as a synchronizing header for every 128 bits of the data, resulting in less overhead. And from Gen 6, moved to 256 bytes fleet with a 1-to-1 ratio, which is a highly efficient and advanced encoding method. We will talk more about fleet later. All right, let's now look at the typical PCI Express system and the components. The components can be root complex, PCI switch, and endpoint devices, and retimer as well. At the very top of our hierarchy, we have the root complex. The root complex is fundamentally what connects the host CPU and the memory complex to the entire PCI Express hierarchy. The root complex can have one or more root ports from which the PCI inverted tree extends towards downstream. Moving down, we encounter PCI Express switches. A switch can be thought of as an assembly of logic PCI to PCI bridges. It has one upstream port, and it will have one or more downstream ports to connect further devices or other switches. These upstream ports and downstream ports are all PCI to PCI bridges. Switches can be cascaded, allowing for complex and extensive hierarchy. Furthermore, some vendor-specific fabric link implementations also allowed more flexible and complex connections. Also, peer-to-peer traffic in the same PCI partition is natively allowed through switches, meaning downstream devices can communicate directly via switch without necessarily going back up to the root complex. Finally, at the end of the PCIe tree, we found endpoint devices. Endpoints are the actual PCI devices that perform specific functions such as storage controllers, NVMe controllers, Ethernet controllers, GPUs, SPUs, and so on. To understand PCI connectivity, it's essential to understand some basic terminologies, port links, and lanes. First, what is the lane? A lane is a fundamental unit. That is one pair of the differential signals dedicated to a transmitter, TX plus and TX minus, and one pair dedicated to the receiver, X plus and X minus. It allows bidirectional communication. The diagram here shows 2 lanes, lane 0 and lane 1, each with its transmit and receive pairs. If these 2 lanes are in the same link, it represents a by-2 link. Next, let's talk about port. A port refers to a group of the lanes located on the same chip that collectively defines a link. Each port represents one end of the physical connection between 2 devices in the PCI system. Regarding the link, a link is defined as a dual simplex communication path between 2 components. This means data can be traveling in both directions simultaneously, and a by n link is composed of the number of the n individual links. It could be by 1, by 2, by 4, by 8, and by 16. The link width is negotiated based on the port width of both sides during the link training. PCIe is structured into several layers, each with specific responsibilities. Starting from the top, we have the transaction layer. The primary rule of the transaction layer is to create the transaction layer packet, or TLP, process the received TLP as well. The TLPs can be memory rewrite, configuration rewrite, messages, and I/O rewrite. It performs the assembly and the disassembly of the packets and optionally carries out high-level error checkings, which is end-to-end CRC or eCRC. This layer is also responsible for storing negotiated and programming configuration information. Moving down, the TLP comes to the data link layer. The data link layer adds a sequence number at the head of the TLP and a link CRC or LCRC for signal integrity at the tail of the packet. Data link layer is also responsible for the initialization and the updates of critical-based flow control mechanism, which is necessary for preventing receiving buffer overflows. This layer also handles acknowledgements for TLPs, sending and checking either ACK or NAK to confirm successful or unsuccessful receipt of the packets. And finally, at the bottom is the physical layer. The physical layer's role is to add the start and the end symbols at the head and the tail of the data stream. These symbols define the boundary of the packets. In addition, parameters like speed, link width, lane reversal, and lane polarity, and so on are auto-negotiated by the physical layer during the link training phase, which occurs at the link training at the state machine, or LTSSM. Okay, we are going to see how the PCIe hierarchy is enumerated. Let's start with the bus device function, or BDF ID assignment, which is how devices are uniquely identified and organized within a PCI Express hierarchy. A BDF ID is a 16-bit identifier composed of 3 parts: 8 bits for bus number, 5 bits for device number, and 3 bits for the function number. Bus number indicates a level in the hierarchy, and each PCI bridge maintains 3 kinds of the bus numbers in its configuration space register. First, the primary bus number. It is the bus number on which the bridge itself locates. Second, the secondary bus number. It indicates the bus number assigned to the immediately next component below the current bridge itself. Third is this subordinate bus number. This register contains the deepest bus number on the downstream side that can be reached after passing through this bridge. The device number indicates different devices or bridges entities locating on the same bus. The function number is for identifying different functions within the same device if it contains. The host probes all possible BDFs in the system by issuing configuration read TLP to read device ID and vendor ID first, and checking whether the completion TLP back is valid or not. Based on the result, host can determine whether there is a device in this position and further check it is an endpoint device or a bridge, or the device is not yet ready, which requires a retry. These probes use a depth-first search algorithm. Based on the probe result, the primary, secondary, and subordinate bus number will be configured properly in each of the PCI to PCI bridges. After then, the host can access the configuration space of each bridge or endpoint by specifying its BDF in order to further configure. The diagram on the right side shows the example of the PCIe hierarchy with the BDFs. Another point, PCIe Gen6 introduced a new field called a segment as an extension to the BDF to overcome bus number limitations in the larger system. Okay, this slide is about base address assignment, which described how the host allocates memory mapped address resources to the PCI devices in the system. Each endpoint device contains memory address window by which the host or the other devices in the hierarchy can access its internal registers or memory via the memory request TLP to perform endpoint device-specific functionalities. Such addresses need to be programmed in the registers called base address registers or bars, located in the configuration space header. Before continuing, we need to know there are two types of the configuration space headers. Type 0 configuration space header. This header type is typically used for endpoint devices. Type 0 configuration space contains 6 generic bars that can be assigned with the 32-bit addresses or 64 bits address by using 2 bars. Type 1 configuration space header. This header type is used for PCI Express bridges. It contains a register named as prefetchable memory base limited and non-prefetchable base limited registers. As we mentioned, the host assigns the memory mapped address ranges for endpoint devices. But how does a memory request TLP load to its destination over the PCI hierarchy? How does a bridge in the switch know whether the target address in a received memory TLP is underneath the current bridge? Which downstream port in a switch should a memory TLP be egressed from? They are decided by the prefetchable, non-prefetchable memory base limited registers of a bridge. They cover the range of the bar addresses for all the downstream devices below the bridge. They act as the apertures. If the destination address of one memory TLP is within the aperture, the TLP can pass this bridge and go into the next stop on the hierarchy until reaching the ultimate device. The host is responsible for updating the base limited register of a bridge while assigning a bar addresses for the endpoint devices. The diagram on the right side shows the structure of the Type 0 and Type 1 configuration space headers, including base address registered for the Type 0 and the memory base limited registered for the Type 1 header. Notice that Type 1 configuration space head contains 2 bars as well, which means the internal hardware resources register memories of the bridge can also be accessed via these 2 bars. Regarding PCI error handling, let's look at advanced error reporting, or called AER. There are two categories of the errors: credible errors and uncredible errors. Uncredible errors is further divided into the fatal errors and the non-fatal errors. If a component identifies a masked error within itself or on its link, it's responsible for initiating the error reporting by generating error signaling messages. So there are three types of the error messages correspondingly. Error credible messages for credible errors, error non-fatal messages for non-fatal errors, and error fatal messages for fatal errors. Error messages are always routed to the loop complex and translated to the platform-specific event by the loop complex. For credible errors, hardware is responsible for credible errors recovery and no software or application is involved. While these errors are recoverable, they may degrade system performance by going down to the narrow width or lower speed. And there is no loss of information with credible errors. The same data is resent or replayed by the hardware. Even though they are automatically corrected, it is necessary to keep track of their occurrences. Error details are logged in the AER registers in configuration space. Additionally, error credible messages sent to the loop complex, informing the system about the occurrence of the credible errors. A typical example of the credible error is bad TLP error, when a TLP got nicked by receiving side because of the packet corrupted. And if the replayed TLP transmitting fails multiple times and exists max replay counts, the replay over error will happen and the link will enter into a recovery state for retrain. Uncredible errors, which are more severe than the credible errors. Uncredible errors cause the data loss and not able to be recovered by the hardware itself. Due to their severity, uncredible errors may require device reset or even re-enumerated by the system. The error handling is specific to the platform. These errors are similar to the system error or SER in the legacy PCIe or PCIe system, indicating a critical problem. The error severity of the uncredible errors can be specified as a fatal or non-fatal in AER uncredible error severity register. The corresponding error fatal or error non-fatal messages will be sent to the loop complex for further handling. A typical example of an uncredible error is a completion timeout. This occurs when a requester sends a non-posted TLP, such as a memory read TLP or configuration read-write TLP to completer, but does not receive the corresponding completion TLP within specified time. This is a critical issue that can cause a system crash if the initiator is the CPU. Some additional mechanisms can be used for preventing system crashes, such as DPC or some other vendor-defined mechanism. We will discuss DPC in the next slide. DPC is a downstream port containment. The name already tells us it is used for error containment on downstream port. How does it work? If a downstream port with DPC enabled detects unmasked, uncredible error or receive the error fatal or error non-fatal messages, DPC will be triggered based on the DPC control register settings. DPC automatically disables the downstream port link when it is triggered, and the DPC interrupt will be sent to the host. The primary benefit of the DPC is that it prevents the potential spread of the data corruption or errors from propagating to the other parts in the PCIe hierarchy. After host system acknowledging the DPC event and performing the essential recovery action, it can clear the DPC triggered status on its downstream port. By this, the link will be brought up again. Furthermore, DPC improves the PCI error containment and allows software to recover from device async remove events. An async remove event refers to the surprise or remove event. Such event can often cause uncredible errors on the link, like completion timeout and surprise down error. DPC ability to immediately disable the affect link upon this errors occurrence. Send a DPC interrupt to the host instead of the uncredible error message, prevent the system crash, and allow for the host to do a graceful handling such event. Okay, let's talk about PCI hot plug. This slide describes the standard hot plug. This mechanism enables the safe, predictable, and orderly addition or removing of devices while the system is running. To support this mechanism, downstream port uses the special hardware hot plug controllers. These dedicated controllers with multiple implemented elements manages power signaling and detection process associated with various events. They ensure that power is applied or removed in a controlled, orderly manner, and that the system can detect when the device is being inserted or removed. This table lists the elements defined in the spec, supporting the standard hot plug. They could be optionally depending on the specific implementations. These elements collectively ensure a robust and safe hot plug experience, preventing data corruption or system crash. Another type of the hot plug we called async remover. This event was often referred to surprise hot plug. It described the act of removing a device without prior notifications. PCI spec defines the hot plug surprise supporting bit in downstream port slot capability registers. If downstream port has its support have this support enabled, surprise down arrow will not be set in the AER where the data link state changes from the active to inactive. In addition, PCIe Gen5 spec recommends handling async remover via the downstream port containment, DPC, rather than hot plug surprise. The reason is that during the device async remover, not only the surprise down error, but also other uncredible errors such as the completion timeout error needs to be handled in a proper way when device is removed. DPC is a robust way to handle this surprise hot plug. Next slide regarding the non-transparent bridging, commonly known as NTB. First, NTB implementation is vendor-specific and it is not defined in the spec. NTB is a useful feature in a scenario where the host in the different separate PCI hierarchies are required to talk with each other. By default, standard PCI hierarchies are independent and isolated from each other. For example, in a diagram, host A is not able to communicate with the host B without NTB. But with NT enabled, host A can access the memory in the remote host B via the NT endpoint bar address mapping, mapping local NT bar addresses to memory address view in the remote hosted hierarchy. This allows the host to initiate a memory reads or write TLP targeting local NTEP bars translated to the TLP targeting physical memory location in the other hosted system. Again, NT feature is vendor specific. Other implementations may not be like this. Move to the SROV. Now let's take a look at the SRV, which is the single root I/O virtualization. SRV is a PCI-based virtualization technology that allows a single physical function devices to expose multiple virtual functions. Physical functions and virtual functions are all managed under a single root complex in the SRV. The hypervisor uses the PF or physical functions to configure the virtual functions, specifying parameters like how many VFs to expose, how to allocate the resources, how to map them to the virtual machines. Once this setup is done, each virtual machine can access its assigned VF directly via PCI Express with the help of the IOMMU. This direct access bypasses the hypervisor in the I/O path, reducing context switching and the software overhead. As a result, virtual machines benefit from the near-native I/O performance, making SRV a powerful feature for the higher performance virtualization. The picture here shows one typical SRV usage. Let's look at the PCI switch in the AI application. Here are some key benefits PCI switches bring to the AI. First, they are fundamental for enabling high speed, low latency interconnection between the various components such as the CPUs, GPUs, SPUs, NICs, and NVMe drives within an AI system. In addition, PCI supports the peer-to-peer communication, which is P2P. This is a significantly advantage of the PCIe in AI application. It allows component devices in the AI system to directly transfer data between each other without needing to involve the root complex as an intermediary. PCIe also enables a flexible topology for the AI clusters with a fabric link support. The complex and scalable AI infrastructure can have more PCIe switches interconnected with each other via fabric link for connecting more endpoint devices in various configurations to meet the specific needs of the different AI training requirements. Finally, PCIe facilitates resource pooling and dynamic assignment. With the PCIe switches, resources like GPUs and NVMe drives can be pooled and dynamically assigned to the different CPU or workloads as needed. This optimizes the resource utilization, ensuring that expensive hardware is full leverage. The picture shows a typical AI infrastructure with scale-up fabric and scale-out fabric. We can see the PCIe switches here connecting multiple components, GPU, CPUs, and NIC DPUs, and so on. Okay, let's go to a few slides to see some new features or enhancement introduced in the PCIe Gen6 spec. Compared with the changes brought about by each generation evolution in previous generations, the difference between the PCIe Gen6 and the Gen5 are significant. Here's just a part of the changes. Prior to the PCIe Gen6, the secondary technology used by the PCIe is non-return to zero on NRZ. But from PCIe Gen6 speed utilized a new signaling technology we called pulse amplitude modulation 4 level or PAM4. What is the difference between the NRZ and PAM4? And what as challenges could the PAM4 bring? In NRZ, each transition represents 2 states, which means 1 bit per unit interval. The signal simply switch between the higher voltage level and low voltage level. PAM4 is that used 4 states, encoding 2 bits per unit interval. Instead of just a higher and low differential voltages, PAM4 used 4 differential voltages levels to represent combinations of the 2 bits, 0, 0, 0, 1, 1, 0, and 1, 1. This allows twice the amount of the data to be transmitted in the same frequency compared to the NRZ, effectively doubling the bandwidth. The picture at the bottom shows an eye diagram of the both signaling mechanism. Because of the 4 voltage levels and reduce the amplitude for each voltage level, 64 gigatransfer per second PAM4 signaling is sensitively to noise and burst errors. PAM4 assumed the bit error rate of 10 to minus 6, which is much higher than the 10 to minus 12 in the NRZ. To address this problem, other changes such as the FEC and the fleet mode have been adopted by the PCIe Gen6. PCIe Gen6 introduced a new mode called flow control unit mode or fleet mode, which is significantly different from a previous mode we call the non-fleet mode now. Why is fleet mode introduced in? To deal with the significantly increased bit error rate, PCIe Gen6 required the forward error correction or FEC mechanism, which works best on the fixed size data blocks. Traditional PCI packs like TLPs and DLPs are variable in size, which is incompatible with the efficient FEC coding. Fleet mode introduced a fixed size 256 byte data unit, allowing FEC to be applied uniformly and efficiently. TLPs and DLPs are encapsulated within a fleet, along with the CRC and FEC bits. The diagram at the bottom here shows the structure of the fleet. It shows a 256 byte block that contains 4 parts. The first is the TLP info, which is the 236 bytes for TLP portion carried. One or more TLPs can be held within a single fleet, and a single large TLP may span across multiple fleets as well. The second is the DLP, which is 6 bytes for data link layer portion. And then the CRC, which is 8 bytes, is used for the error detection across the fleet. And ECC, which is 6 bytes, is used for the FEC, allowing the receiver to correct a certain number of the errors within the fleet without needing a retransmission or replay. Fleet mode is mandatorily required when operating at Gen6 speed, but it doesn't mean only works with a Gen6 speed. If fleet mode is enabled, it is enabled for all speeds and remains enabled until a reset or a link down. Fleet mode can be disabled, but obviously this will limit the link speed up to Gen5. Finally, the NAK protocol and the retry mechanisms in the fleet mode are now on the fleet level, and the NAK and the NAK DLPs are not used anymore. This slide talks about replay mechanisms in fleet mode. In fleet mode, only the TLP portion in fleet data are replayed, not the DLP portion. The DLP field in the retried fleets reflects the latest DLP payload, and it's likely not the original one in the naked fleet. A new replay scheme is introduced with the PCIe Gen6 in the fleet mode called Selective Replay. This is an improvement over the original standard replay scheme. Let's look at the 2 schemes. The first is standard replay. In standard replay, if the receiver of the link partner naked a fleet with a particular sequence number, indicating the fleet with that sequence number is the latest good one received, and the fleet with the next sequence is the bad one. The transmitter then replays all the fleets after their last good one. That is the simpler but less efficient method, as correctly received fleets that came after the error one also get retransmitted unnecessarily. For selective replay is a more efficient mechanism. When a receiver nakes a fleet with a sequence number, the transmitter only replays the particular fleet. It improves the link efficiency and reduces the latency. To make the selective replay work effectively and maintain the data order, the receiver needs to keep following a valid fleet in its receiver buffer before it receives the correct replayed fleet for keeping the orderly lure. Another new feature in the PCIe Gen6 is the shared flow control mechanism. This mechanism aims to optimize the receiver buffer resource utilization for virtual channels. In earlier generations, flow control resources were provisioned separately for each virtual channel. This means each VC has its own dedicated flow control resources. However, in practice, buffer usage in this way is inefficient. To address this, PCIe Gen6 Flip mode introduced a shared flow control mechanism. In this model, there's one additional common pool of the flow control credits. This improves the utilization efficiency and reduces the cost of the supporting multiple virtual channels. Shared flow control mechanism can only be used in flip mode. When only one single virtual channel is implemented and if there is no merged, all flow control uses a shared credit, no dedicated credits. A transmitter can indicate to use a dedicated credit when transmitting a TLP, even when shared credit is available. It can be indicated in the prefix. This slide introduces the L0P. L0P is a new port saving state in the PCIe Gen6 that allows two connected devices to shut down some of the lanes in the link, such as downgrading a by 16 link to by 8 without going through a full recovery process. In previous generations, changing the link width required a link recovery process. L0P provides a lightweight but quick way to adjust link width for power saving purpose without affecting the transmitting on those rest of the active lanes. So here P likely means the partial. The support for the L0P is negotiated between two devices in the configuration phase during the link training. Once L0P is enabled, any port can request a link width change by sending up to 3 identical link management DLRPs within 5 consecutive flits. This can be downsized to reduce the number of the active lanes or upsized to the more lanes, even to back to the full negotiated of the lanes. Okay, we have finished all today's slides for the PCIe. Hope this is helpful. Thank you.
Thanks, Martin. I appreciate the details going through everything. And we do have a few questions that have been coming in. I've been answering a majority of them as they have come in, but we'll give you a chance to speak to those as well, since you're the presenter and the subject expert here. The first question is, how does PCIe address take place when it's part of a same device versus a distributed scenario?
For the, let me check the questions. So you mean the PCI address takes several PCI endpoints as part of the same device first distribute? I don't know what's a distributed scenario.
Distributed scenario.
I'm not for sure or for clear about the distributed scenario. So means part of the same devices.
So in a distributed, like multi-host environment, I believe that's how I understood the question.
Okay, so from the PCI spec, that the one endpoint device can only be owned by the single upstream device or the low complex. So if it needs to be addressed by the different PCI partition or PCI hierarchy, it needs the device to be like utilize some vendor define the mechanism like dynamic assignment to dynamic one endpoint device from the PCI partition A to the PCI partition B. Then this event could be treated as a hot removed event in the PCI partition or hierarchy A, and will be hot added in the partition B. But it cannot be utilized by the both of the host at the same time.
Great. Here's an interesting question as well. So, are you aware of any work in progress on PCIe over optical interfaces and PCIe over Ethernet?
Actually, I'm not experienced on this scenario, like PCIe over other physical layers.
Yeah, I'm not 100% sure on that either. I think there is some work going on in Gen 6 to include PCIe over optical. I'm not sure about Ethernet myself. We'll do a little bit research on that, and we will get a answer in the blog that we could do that with. Another question here: can LOP downsize to lower than 8 lanes?
Yes, that's true. Yeah, it could be to the at least by one.
Next question then, when speed negotiation changes the speed, for example, from Gen 6 to Gen 5, or vice versa, is there a device expected to switch into and out of FLIT mode automatically based on the speed negotiation or some explicit configuration changes requested by root complex?
Based on the negotiation result. So even even the PCI Gen 5 speed, if both of the side enable the a fleet, then and the fleet is negotiation, then the speed Gen 5 speed will still work on the fleet mode.
And we have time for a few more questions here. Does PCIe spec have a defined register available that indicates the current BER rate, or would that be vendor specific?
I think it is vendor specific. I'm not sure about this question, so let me just check later. Yeah.
Okay,
Offline.
yeah, we'll get another answer out to that then in the blog to make sure we're correct on that. And another question, are there any efforts to standardize MR-IOV for device sharing over multiple host fabrics?
I think for the MILV, that there is very few implementations or very few users in the market. So I think it is in the PCI spec. There's also not much mentioned about MILV. So I think the most of the IO virtualization is for the SRLV. I'm not sure how many devices just use implemented with MRLV. And MRLV also requires the switch to implement this feature to about the MRLV.
Another question here we have, any ongoing projects or working groups that are using PCIe for composable infrastructure?
I'm not sure about this answer. Yeah. Yeah, we can check later.
Yeah, I would think that there are. We'll do a more complete review of that question and get a good answer for you guys in the blog. And let's just see if there's any other questions that we're missing. Okay, so there's one in SRIOV. Is the hypervisor a generic system driver, or is that a vendor? Someone put another question that just jumped down. Or is that a vendor provided driver? Sorry about that. Let me repeat it. In SRIOV, is the hypervisor a generic system driver, or is that vendor provided driver?
I think both. I think both. That is the hypervisor is. I think it is system depends on system implementation. So yeah, that could be utilized both.
And does scalable IOV require any changes to PCIe?
Scalable requires change to the PCIe. I'm not sure about this question. What is the question really means? So I'm not sure about the answer right now. Yeah.
Okay. Another one we can get to in the blog. And it looks like we've got another one here. What is the difference between SRIOV and the latest SIOV?
Actually, for this answer, I'm not sure. Yeah, I need to check.
Okay, we'll do a little bit of homework. Good questions coming in. Sounds like we've got a pretty technical crowd out there. We appreciate everyone joining us today and making this presentation interactive by asking all the questions. We just want to go over a few things real quick. As you're leaving, you'll be asked to rate the webinar. Please do so and provide us with any feedback that you have. As mentioned at the beginning, your feedback will give us the ability to make sure that we are providing the best information we can to you. Also, if you'd like to revisit the material at any point, the recording and slides will be made available to the SNIA Educational Library, which can be found at snia.org/educational/library. As mentioned, the Q&A blog will be posted. That will be at sniablog.org. Usually takes us about 2 weeks to get those out, but we will include all answers, even the ones that we couldn't get to today. If you're interested in staying up to date with our latest news and events, you can follow us on X, which is formerly Twitter, at the @snia.com, SNIA, so at SNIA. Thank you very much for joining, everybody. We appreciate the questions. Thanks so much, Martin, for giving us all the technical detail. Good job getting through a long slide deck today.
Thank you. Thank you for everyone. Thank you.
Great. Goodbye, everyone.